Hopefully you can hear me all right. Thank you so much for coming. It is my great pleasure to introduce our first speaker. This is Kenny Glotfelty, who has been with us at the CfA working at the Chandra X-ray Center for almost 30 years. Kenny began his SAO career working with the CXC calibration team and ACID instrument team supporting Chandra pre-launch activities. He then moved onto leading the software development team responsible for science processing pipelines and data analysis tools. Kenny's current position is with the Science Data Systems Group, where he supports Chandra and its end user Chow software package, and I'm sure many of us have used it who are in this room today. So before working with us at the SAO, Kenny completed his master's degree in electrical engineering with a specialization in communications and signal processing from Northeastern University. And Kenny's professional interests include image processing algorithms and topics in the user interface and user experience space. And the title of Kenny's talk today is Celebrating SAOImageDS9 2024 ADASS Software Prize. So thank you very much, Kenny. Take it away.
Thanks. Is this working? Okay. So as most people know, DS9 did win this year's ADASS Software Prize. They've only been giving it out 5 times, and CfA has won the last 2. So I think as a member of the CfA, we should all be very proud of that. In particular, Bill, Joy, and Eric Mandel should be particularly proud of their software. At the time the prize was announced, it wasn't clear due to the Chandra budget whether Bill would be around to provide to give the talk, so I was asked to do it. And then I've been asked to reprise it here for the local folks. So I'm going to start with a little bit of history. Some of you know this, some of you will probably cringe at this. This is the original SAO image circa 1990. This was developed by Mike Van Hilst under Eric's direction. It was one of the first X11 applications. Actually, before this, most of the computer programs we ran were using terminals, and all you had was a terminal, and there was no fancy graphics windows. And it was about this time that the windowing systems came to be, and this was one of the first applications that was available. Then in the mid-90s, the next generation of DS9, or the next generation of SAO image was released, TIG. We don't talk about it much. It wasn't very particularly well received by the community, but it did have some technological advances. So it was able to be controlled using XPA, to be controlled using an external library, and you could customize it. So you could add your own plugins and you could add your own analysis buttons, kinds of things. Then around 1999 is when SAOImageDS9 was first released. It's kind of, for a very long time, DS9 was released in betas, and it never actually came out of beta until like DS9.7. So when we talk about DS9, it was all beta releases until the very, almost the very end. So DS9 was originally funded as a NASA Applied Information Systems Research Program. And I had to write that down because I can never say all those words. And Eric Mandel was the PI. In the final write-up, there's a very prophetic comment at the very end that with the support of its further development being provided by SAO, we are confident that DS9 will soon become the de facto image display standard in the astronomical community, March 2000. And we are here celebrating DS9 24 years later. So I think Eric made a very prophetic and accurate comment. But there's another part of this. With the support for the development being provided by SAO, there's a recognition that DS9 was not done. That there was more to do, that there was more that it could do, that there was more that needed to be done. And that was recognized internally at SAO. And I always talk, if you ask me, I'll say, a single software or a single developer on a piece of software is almost always the best. Groups confound each other. That's wrong. A single developer is good, but you always need somebody to, provide the buddy. And in this case, that person was Steve Murray. For the better part of a decade, Steve Murray, the late Steve Murray, I should say, was the man behind the man behind Bill and Eric, making sure that SAO was providing the funding for DS9 continuous development. So any talk about DS9 is not appropriate without including Steve in the discussion. So what does DS9 do? Probably everybody here knows most of these things, but you may not know everything. So DS9, what does it do? I tried to make a single graph that shows all the different capabilities, and you can't. You can't list everything that DS9 does. Obviously, being in development for 24, 25 years, there's a lot of things it can do. So I'm just going to kind of show some examples. I call this regions because this is an isotomy image. So fact number one is that DS9 is one of only 2 or 3 applications that can directly display event lists. Almost all the other imaging applications out there, you can't display an event list, you have to bid it into an image first. So still to this day, high energy is being ignored in that respect. My comment at ADASS is tables are images too. But I said that 12 years ago, they still didn't listen to me. So a couple of things. So this is DS9. What you're seeing is the advanced view. This is my one contribution to the DS9 code base. If you go to advanced, and if you can read Japanese, one of these things says view, supposedly. View advanced, this is the latest analysis view where you have a bunch of icons where you have single click access to various features. DS9 is localized, I think, to 8 countries or 8 languages, I should say. You also see things like you can add custom keywords to the info panel. So here I added the telescope keyword, which it tells me that it's atomic data. This is a custom color bar, so this is one of the default color bars of DS9. So there are many ways you can customize things. This is something I think gets underlooked all the time. DS9 does do catalogs. So if you're doing catalog work, you can load a catalog into DS9, whether it's a VO table or a fixed file or a tab separated ASCII file kind of thing. And you get a nice catalog table thing here. The markers are conditional. So in this case, the green markers are variable sources and the yellow markers are not variable sources based on information in the catalog. You can plot columns in the catalog. And if you select a row in the catalog, it gets highlighted to the plot, it gets highlighted to the imager. So that's this linked view thing where all the things talk together. And if you select multiple sources, multiple lines get highlighted and then multiple plot symbols get highlighted. You can also do all sky data using HealPix format. This is a IRAS HealPix all sky image and galactic coordinates. And then the coordinate system that's overlaid is ICRS. So you can do all sky things as well as single observations. DS9 does analysis plugins. This was actually a talk at ADASS 3 years ago before the DS9 talk. So this user has a whole set of Python plugins. This particular plugin is doing a focus test or a focused optimization, determining best focus. So he has multiple frames. These are DS9 plots that's showing the size of the source, and all this analysis is happening in the background in Python. So these are both DS9 windows, and then he also has a 3D plot that shows up. That's it's VTK or something within the Python machine. So they all work together. DS9 also does do 3D, does 3D rendering. This is the vertical view, in case you haven't played with the views. This is the vertical view. And it also uses a different color theme, so you can see that it's more, it's like a peach color or a cream color. And while this is a nice kind of staticky thing, DS9 also does movies. So you can output from DS9 directly a animated GIF or a MPEG movie. In this case, it's a showing the 3D slices through the data. This is XMM data showing RA, DEC, and energy, or X and Y and energy. And you can see the iron lines. This is a cassette, just to make Paul happy. You can also do movies using multiple frames. So if you have a whole bunch of images of the DART mission coming in to push the asteroid out of the way, you can create a movie using those. And you can also do a movie where you take one of these 3D things and you start rotating it. And these are the pretty images that everybody likes to see, which is why it gets included. The newest things in DS9. So there are two features that are being shown here. One is we know DS9 alrighty, so
Underneath, like that,
Yeah.
some panel, if you put slides in there,
Ah,
if you press.
okay. Can you go a second with the mouse on the screen? Okay? And click on slides. Maybe.
We get also the meeting is recorded saying on Zoom.
No.
So we need to.
Yeah,
you
yeah,
press
we'll
the-
we'll do it. Okay, can you now go here and go to the win? Okay, now?
Yes.
okay. Okay. Yeah, okay, so illustrate mode, what that lets you do is it lets you attach graphics to the display that are fixed within the display. So if you pan around, if you move around, the graphics stay there. So in this case, what I've done is I actually made this grayscale image of the supernova in DS9, saved it as a PNG, exported it as PNG, and then loaded it back in as a PNG into DS9 so I could create the inset. So that's how that was created. So I promised some quick tips along the way. If you ever take a screenshot of DS9, what you might find is that the magnifier and the coordinates are blank. And usually that happens because the application loses focus, and then when it loses focus, then those things no longer get drawn. If you press F, it actually freezes the display. So if you need to stop the coordinates from changing, or you want to stop the magnifier from moving around, just pressing F will stop it from updating, and then pressing F again will start it updating again. That's actually in the documentation. Some other things I'm going to discuss will not be, but so who uses DS9 and for what? I tried to come up with a really pretty picture. NASA SMD has a great image showing all the fleet of missions that they support. That all works, that's NASA. Unfortunately, it does not include, the NASA does not include, ESA and JAXA and all the other space agencies. And that doesn't include NSF and all the ground-based observatories. And that doesn't include all the telescopes, organized by consortiums and all that kind of thing. So rather than try to show all that, I just made this cheap little word cloud. This I find astonishing. This is the number of DS9 downloads per year for the last 5 years. And it's downloaded between 30 and 40,000 times a year. Just for comparison, I believe, the last time I was told, the number of people in the AAS registry was 6,000. So that means everybody in the registry is downloading it 5 or 6 times. Of course, that's 2003 is actually an anomaly because we lost some of the download logs, but it's about 3 months of logs, so we would be back up in the 30 to 40,000 range. That's truly astonishing. We also see that the largest fraction of downloads are for Windows users, which is not what most of us tend to use. So that is pretty indicative that a large number of students, either elementary or middle school students, are probably using DS9 as part of their assignment work. We don't have actual curriculum that shows that, but we have a lot of citizen science projects that show that it's being used in amateur arenas. In just 3 months, at the beginning of the year, we took a snapshot of the download logs and we looked, where is DS9 being used? And in 3 months, it was being downloaded to 101 countries. The US was the highest at 35%, and then Europe, Australia, India, and Japan made up the top 10. For those of you in the funding agencies, China and Russia were 11 and 12. We don't say that, that's why we stopped the top 10 and didn't necessarily advertise that because that could be politically challenging. Where is DS9 being cited? Everybody in software, this group is a different group, but everybody in software knows software is not cited. Just as a general rule, it's hard as pulling teeth to get software to be cited. But it's actually not so bad. So these are DS9 citations. The pink curve is actually doing a full text search for the word DS9. It's not entirely unique, but it's pretty unique within the astronomy subgroup. And then the green curve is the citations to Bill's 2004 ADASS paper. So obviously there are no hits before 2004. One encouraging thing though is that the number of citations to the actual paper, the percentage has been growing. So kudos to people who are actually citing the software. Oops. Yeah. What are those people doing with it? So if we look at the ADASS or ADS search keywords that come up, by the way, this is really hard information to get out of ADS without going into the HTML to pull it out. But the number one, the highest number of papers are about X-ray astronomy, which kind of makes sense given that X-ray astronomy can't be done without DS9 or another imager that can display an event list, which there are, like I said, 2 or 3. So rather than go into all of these different things, I just pulled out a couple of truly unique uses of DS9 that I found to be quite fascinating. This was a help desk ticket from 3 years ago. If you can't read it, it basically is asking Bill, can you include a new catalog? Because I use DS9 to check coordinates for JWST targets. And I would love to tell you who this person is, but I can't. Yeah. If you ask me some other time that I'm not in public, I will be happy to tell you. But they're a very avid DS9 user, and very senior, and we'll just leave it at that. Yes, 5 minutes, okay. So ADS is great. We all use ADS for everything under the sun. But when we were putting together proposals for DS9, what we did was we kind of broadened our search, and we looked to Google Scholar and typed in DS9 in Google Scholar and said, okay, what's in there? And what we found was this, or one of the things we found was this. which was Darby et al. We're using DS9 to check mask efficiency for COVID-19 research. And we're pretty sure it's the right DS9 because it's talking about DS9 color BB color mode, which I think, or color map, which I think we are all familiar with. This one is fun. For those of you probably recognize DS9 by now, sitting here in the background. And if we pull out, this is actually a frame from the popular show Big Bang Theory, which some of you might know. And this is Raj, and this is his telescope room, and you can see DS9 is running in the background. You can also see there's another DS9 running in vertical mode on this side. So kudos to the set dresser who knows somebody in astronomy, and your code is popular when it actually hits pop culture. Another little quick tip here before we get into the finish. If you like DS9 and you need to pan around, you will usually either move the panner up here or you can center click and it will recenter wherever you click. That all works, but we're used to like Google Maps where you click and drag to move the image around. And you can do that if you go into your preferences and drag to center. You can then do a Google Maps style click and drag instead of having to click to recenter it. So I'm going to skip all of this, unfortunately. And we'll talk about the future. For those of you who don't know, Kobayashi Maru is a reference to Star Trek, as is DS9, in case there was any doubt in your mind. Kobayashi Maru is the unwinnable command scenario. It is the test that they give captains where there is no way out, and they want to see how you react to that situation. And unfortunately, DS9 is in that situation. So DS9 is 100% funded by CXC, and this group in particular knows all the CXC fund that's been happening over the last year, and will repeat next year. On top of that, Bill is planning to retire. He would have been retired this year, but I don't have a date. I don't have a month, but I would not expect to see Bill around campus this time next year. We've had one NASA and 2 CFA internal proposals that were not accepted for funding. The NASA was to sustain DS9. The 2 CFAs were to begin the process of developing the next generation. I put this here because whenever it was announced at ADASS that I'd be doing the talk, it was suggested that I was taking over active development of DS9, and I won't be. My job is going to be more of a curator, so I'll be able to do builds and that kind of thing, but I'm not going to be the active person supporting it. So that's it. We can do questions.
Okay. Thank you.
Thank
If you
you.
want to see pretty pictures, I can go back to there, just because the data just is pretty picture.
Thank you for the nice talk. So we have time for questions.
I just have a request. That hopefully is not too rude. So I think you had some slides on some kind of like a quick, turn into how to use it. Are you able to share it with us?
I can make the slides available, yeah.
Good, thank you.
Any other questions? Okay, so I'm gonna ask a question. Which feature that is not currently implemented in DS9 would you have liked to see be implemented, or you would like to see implemented in the future?
I'll bring this just to kind of show. Well, I'll show this first. When we talk to Bill, whenever he starts talking about, what the features are that he goes through, new features only take up 25% of his time. That's all he gets to implement new things. The rest of the time is, help desk and maintenance and all those other things. And there's there are some very large challenges that will be affecting DS9 in the next, well, starting this year. There's a change coming to Linux is moving away from X11, Linux is moving towards Wayland. There's an interface layer that provides communication between the two. Unfortunately, it does not behave well. So, for example, DS9 will not work very well on Fedora 20, or sorry, Fedora 40, or Fedora 41, which is also just released. Mac OS is a pain in the, whenever dealing with unsigned applications and third-party applications, they're actively seeming to want to move in a direction that closes off development that doesn't go through the App Store. So that affects a large number of our people here. And Windows users, I don't really, not so worried about Windows users in general, except to say that DS9 does not support ARM on Windows and the ARM processor, so the M2 equivalent processor. And that's going to be a very big challenge in the coming years because they're a whole lot, they require a lot less energy, and laptops will want to keep getting thinner and thinner and smaller, and the only way to do that's going to go to ARM. That's not going to be a feasible solution. So I'm not looking necessarily for features, I'm kind of looking at, right now my brain is on, we've got these things where there will be no version of DS9 that will run on these systems. I had a question from ADASS about using PyDS9, and my answer was kind of the same thing. It's like, well, PyDS9 isn't supported either right now. We're not planning to, mostly because there won't be a DS9 for it to run on.
Any final questions? So to end on a more positive note, please raise your hand if you use DS9. Thank you so much, Kenny. Let's thank Kenny again.
What you guys got to do?
You are still sharing? Núria, can you share your screen?
Yes. Can you see it?
Yes, let me. Okay.
Yes, we can see the screen.
Just a second, let me do a couple of things. Is it good there?
Okay, so it is my pleasure to introduce our second speaker for today. Núria Torres Albà is currently a Gecko Fellow at the University of Virginia in Charlottesville, in Virginia. She obtained her PhD in 2019 at the University of Barcelona in Spain, and then she moved to Clemson University for her first postdoc. Her research is focused on active galactic nuclei and their surroundings across the electromagnetic spectrum. In particular, she has worked on X-ray analysis of luminous infrared galaxies and quantum-thick AGN in the local universe, as well as modeling of gamma-ray emission producing the interactions between AGN jets and obstacles. Currently, her main research centers on using obscuration variability to constrain the material distribution surrounding supermassive black holes. So today, Núria will be talking about obscuration variability in local AGN. So thank you very much for joining us and for chiming in remotely, and the floor is yours.
Yeah, thank you all for having me. My name is Núria. I've recently started as a Gecko Fellow at the University of Virginia, and today I'm going to be talking about a work that I started with my students when I was still at Clemson University, and it centers around studying obscuration variability in local AGN. And as it's already been stated, the objective of this project is to find a way to constrain the properties of the material that surrounds the supermassive black hole. And by that material, we essentially mean the torus, or anything between the supermassive black hole and torus scales. So our current understanding of the AGN torus has moved from a more simple, sort of uniform, donut-shaped structure into a more realistic, most likely clumpy structure. And we know this from different clues from studying infrared emission. One of them is differences in optical depths between CfA1 and CfA2 galaxies. And another one is just direct infrared SED fitting, in which clumpy models simply reproduce the spectra of AGN a lot better. But we also have clues into this phenomenon from an X-ray perspective. And one of them is the direct observation of occultation events, which can happen at any time scales from less than 1 day to timescales of years, essentially. And what do I mean by an eclipsing event or an X-ray eclipsing event? Well, essentially, we have our supermassive black hole, the accretion disk, and the corona. We don't know exactly where it is, but very close to the supermassive black hole. And there's something between us and the AGN that crosses into our line of sight and changes the level of obscuration. So we go from a certain base level obscuration before this occultation happens into increased obscuration as this occultation is starting, to a peak of obscuration, back down again. And once the event has finished, we see our baseline, or we recover our baseline level of obscuration. And based on the exact shape of this occultation event, we can actually infer the properties of this material. And by that, I mean the density profile of this obscuring cloud, its possible velocity, distance to the supermassive black hole, and so on. So this is one of the best ways to directly infer what is happening very close to the supermassive black hole. But how do we exactly do that from X-ray observations? Well, essentially, when we don't have the occultation event at our baseline level of no obscuration, we see the X-ray spectrum in the shape of a simple power law. And as the obscuration is increasing, we see that we see this obscuration feature in the X-ray spectrum that starts at the lower energy range. And at the peak of obscuration, when obscuration is higher, we see that the suppression of X-rays extends to even higher X-ray and photon energies, right? So harder X-rays. And the exact shape of this curve that I'm showing here directly correlates to the very exact amount of obscuration in our line of sight in a very precise manner to show a more direct spectrum. So, well, not real data, this is simulated data to make things easier and neater. These are two different X-ray spectra of the same source. The only thing that has been changed here between one observation and the other is the amount of obscuration in the line of sight. And we're using a full band coverage. So this is simulated simultaneous XMM and Nooster to recover the parameters as best as possible. And indeed, if I feed the simulated data, I recover my input, which is shown here in the white crosses. And I can truly tell that these two observations are incompatible in terms of obscuration or column density, NH, at the level of 3 sigma, right? So there has been obscuration variability. The advantage of this type of measurement in X-rays is that it's very precise. So we can get a very good idea of the exact amount of obscuration or column density in our line of sight. Now, this has actually been done quite nicely in previous works, and I'm showing here one of the best examples. This is a work by Markowitz et al. In 2014, and it shows an individual eclipsing event, essentially. The top panel is showing a flux ratio between hard X-rays and soft X-rays as the days are passing. And the three bottom panels are essentially showing the same data. So obscuration as a function of time, NH as a function of time, but there's an attempt at fitting the profiles observed with different models, from a uniform sphere to two uniform spheres, to a double beta profile, and finally at the bottom, which is the best fit, a uniform density shell. So essentially a shell of material that is circular, or a sphere that is kind of empty in the middle, right? Or a lot emptier in the middle than at the sides. That would be the best fit. So from type of things like this, you can actually get a very good idea of the distribution and properties of the obscuring material. However, anyone in the audience, I think is going to be most people familiar with X-ray observations, will know that we don't really have these type of monitoring programs in X-rays that are essentially looking daily at nearby AGN in X-rays to give us this information and these values of obscuration every day. In fact, the most extensive study that exists of this type is the one I just cited by Markowitz in 2014, and they continuously monitored 8 objects only for 17 years, and they only saw 12 full eclipsing events, right? If you separate that further into type 1 AGN and type 2 AGN, it turns out we have 8 occultation events for type 1 AGN and for type 2 AGNs, we only have 4 events. And this is what I'm showing here. In fact, from these very low number of events, a probability density function of an eclipse happening at a given time scale, so with a given duration, is generated. And these probability density functions are currently being used to calibrate clumpy Torres models, both in the X-rays and in the infrared. So obviously the problem with this is that this has the potential of being heavily biased because it's calibrated using only 12 events that then are also further separated into type 1 and type 2 galaxies. So it's not ideal, right? There is room to do more. Something else that I think is particularly interesting, oh, I don't think this doubling up should be here. Sorry about that, I don't know how it happened. But essentially, the important point here is that less than 50% of AGN are obscuration variable as determined by a bunch of different studies in large-ish samples, say that contain 10, 20 AGN or on that order. And the question to ask here is this normal? Is this normal under the assumption of a patchy torus? So if it's patchy, why aren't all AGN obscuration variable? Why is it systematically less than 50%? So from these questions and needs is born the NH variability project that we started that has the objective of exploring the AGN torus.
Núria,
Yeah?
we cannot hear you in the room.
You cannot hear me?
We don't know what happened again.
I didn't do anything.
Something happened with our broadcast here. Okay.
Zoom hears me then.
Um,
All right. So, yeah, can I go ahead?
Just one more second, sorry. Well, I think you can go ahead. Yeah, we're just doing minor changes. You can go ahead. Yeah, you can go.
Okay. So from these open questions, this obscuration or NH variability project is born with essentially the objective of exploring the AGN torus by characterizing the typical obscuration variability or delta NH for a typical time difference or delta T for local AGN. And we want to do this by determining the obscuration in the line of sight at different epochs for a bunch of different AGN by using different observations available in the archive. So essentially, instead of using time-consuming monitoring campaigns, we're going to take advantage of all of the years of archival X-ray data that can go back, 20 years easily nowadays with Chandra. So we started by observing this sample previously analyzed by one of our students, well, student back then, no longer a student, Shuri Zhao, who studied a sample of 100 local AGN that were BAT detected, which is good for us because BAT detected means just simply bright. So they have a very good chance of having good quality archival data, and they all turned out to be Compton thin, which is good when trying to determine obscuration because Compton thick sources or very heavily obscured sources will present very large errors when trying to determine their obscuration. And all of them have at least one Nuster observation, which is again very good for us because it will help us determine some of the parameters with better precision, parameters that we maybe don't expect to change between one observation and the next, like, for example, the inclination angle at which we are observing this AGN. And this is an example of one of the sources that Shuri analyzed. And as you can already see, since Shuri was also using soft and hard archival X-ray data, he found that most of the observations he was using were not simultaneous, and therefore they didn't always match. So as an example, between this XMM and Nooster data for the same source taken years apart, there's clearly a mismatch that is best fit with a change in obscuration. Now, what Shuri found is that 31 out of the 100 sources he analyzed required some form of variability, either in obscuration or in intrinsic luminosity. We decided to take all of them as this possible obscuration variable sample, because when you only have 2 observations and the data quality is not fantastic, sometimes it can be hard to distinguish between one type of variability and the other. So we start from this sample of some 30 sources that now have multiple observations in the archive. And so far, what we have done is just compile all of the data available for these sources and simultaneously fit all observations for each individual source using, modern self-consistent Torres models that I am mentioning here, and that can account for other components of the X-ray spectrum that are not really relevant for this talk today. I just want to highlight in this example spectrum that I'm showing here that this change of spectral shape that you're seeing in the 2 to 10 keV range, this change of curvature between these 3 different spectra, is indicative of a change of obscuration, right? So this is what we're trying to model for all of these AGN. And so far, what we have worked on is with the pilot project published by one of my students, as well as 2 main papers that contain 24 sources in total. And apart from that, we also go for in-depth analysis or monitoring campaigns of particularly interesting sources or sources that have a lot of observations. All of these works here have now either been published or submitted and are in refereeing process. And we've analyzed a total of 27 sources and more than 150 observations. And I'm just going to share some of the main results of the project, as I obviously cannot talk about every single thing that we did in these papers. But I would say one of the main results that we find is that we can only truly confirm that there's obscuration variability in 11 out of the 27 sources that we analyzed. And I want to remind you all that because of the selection that we did that I explained a couple of slides ago, I purposefully biased this sample towards things that are expected to be variable. And despite that, we still recover this result that we can only truly ascertain variability in terms of obscuration variability for 40% of the sample. For 11 sources more, so another 40% of the sample, we found that instead, they were a lot better explained with intrinsic flux variability only. And for 5 sources, we really could not determine which of the 2 variabilities was responsible for the changes in the spectrum. So this could potentially be obscuration variable as well. And if we were to add them all up, this would add up to 60% of the sample instead of 20%. I also want to use this chance to highlight that just because we don't see obscuration variability in a bunch of X-ray observations does not mean the source is not variable, right? There's always a possibility that we did not catch it vary. But we can still use the information of the number of sources that we see vary to calibrate models, and I'll go into it in a little bit. Something else I want to highlight is the big differences that we see in sources that, a priori, we don't have any reason to suspect should be different. For example, this is an example of a very variable obscuration variable source, NGC4388. You can see that it has various epochs with very different obscuration. But if we look at this other source, set by one of our students, he has, I think, 11 or 12 different observations for NGC6300, and it is essentially compatible with always having the same level of obscuration. If you fit this with a flat line, it turns out to be a very, very good fit, right? So these 2 sources behave in a very, very different manner. So it makes you wonder, is there something intrinsically different happening in these 2 AGN? Something else that we are doing or have started to do now that we have enough AGN in the sample is doing plots like these. What this is showing is putting all of the sample together, and for all of the observation pairs that we have available, we calculate the percent of variable observations, or essentially the probability of finding obscuration variability for a source as a function of the time separation between the two observations available, right? So how likely is it that you'll see obscuration variability as a function of time? That's what it is. And as you can see, we see a very clear trend so far of the probability increasing with the timescales of observation, which is saying something about the intrinsic distribution of material surrounding these sources, right? I'm also showing another plot that is interesting, doing the same thing, but instead of the probability of finding variability, it is when we find variability, how much has the source varied? And what's interesting in this plot is that it's essentially we see no trend, right? This is compatible with always having the same average variability independent of timescale, except for at very short timescales. So a possibility is that perhaps we're only seeing broadline region cloud eclipses when we are looking at very short timescales, and that this is maybe the typical obscuration, the typical column density of a broadline region cloud. Alternatively, perhaps we're just barely seeing an eclipse when that's happening because the cloud is still passing. It just takes more than 10 days to go across our line of sight, and we only see a small change in its density profile. In order to explore this better, what we have started working on is the creation of 3D models that look somewhat like this. And what we can do with these 3D models is essentially rotate the whole thing, which is equivalent to a change in time, right? To making the torus move, and check if a particular cloud distribution can actually reproduce these patterns that we are seeing. And what I say by that, I don't only mean these two patterns in these plots here, but also can we reproduce what we see in individual sources with the same model? For example, can the same cloud distribution with a change of inclination angle explain both these sources? Or do we actually need to make a very different assumption about the distribution of the material to be able to recover these individual source observations? So this is something that we started working on, and we hope to have results for soon. Apart from that, another project that I want to highlight that's very closely related, something that's being done by one of my students at Clemson, Isaiah Cox. And what he did essentially is devise a very quick method of using two different hardness ratios by finding out which bands with combinations of energy bands in an X-ray spectrum are ideal to find spectral variations that are associated to obscuration variability. And what he's plotting here for one of our sources is just this combination of hardness ratio for each observation. And essentially, any source in here that does not overlap with each other means that there is a variability in the spectral shape between these two observations, right? So this is a very quick way to figure out just from counts, essentially, which sources are likely to be obscuration variable. And from this project, this student is already working on obtaining data from the whole of the Chandra archive for AGN within a redshift of 0.1, which I think is a few hundred, and to determine the first lower limit of obscuration, of the number of obscuration variable AGN in the local universe. And again, this is something that our cloud distribution model is going to have to be able to reproduce. So stay tuned for all of these results to come, and I'll leave you here with my summary.
Thank you very much, Núria, for the wonderful talk. We have time for questions.
Online, there's one.
Yes, thank you, Constantina. Yeah, I missed that last time, so.
It was Ernesto, I think.
Ernesto, do you have a question? If so, you can unmute yourself.
Yeah, all right. Thank you for the great talk. I was wondering what's the mass range of AGNs you're working with, and how do you expect this to scale to lower masses?
Oh, that's a very good question. So we're mostly working with very local AGN, all in sort of the same range of luminosities. And I've only checked for the sources essentially within this largest first project, right? There are like 24 or so. And I would say, if I remember correctly, the black hole masses are all around the order of 10 to the 7, or a few 10 to the 7. I don't think they, or at least most of them, reach 10 to the 8. That's more or less the range we're currently exploring. I think it'll be interesting to, when we have enough data, actually separate our results into mass beams, and maybe even better Eddington luminosity, like Eddington rate beams, and see if there's a correlation between the distribution we are seeing and the luminosity or accretion rate of these sources, because some works have been found that insinuate essentially that the stronger you accrete, the more you push back the material around the supermassive black hole. So there could be some intrinsic differences in the distribution of material, perhaps due to that. But at the moment, we do not have enough data or enough galaxies in the sample to actually answer this question. But we're already working on expanding the sample, first of all, into a nicely sized control sample, so one that is not selected to be variable, and then expanding it to the whole sample of at least the sample of 100 sources that was initially analyzed by our student. And maybe then we'll be able to say something about this.
Thank you.
Any other questions for Núria in the room?
Yes.
Could you explain the 3D model a little better? I didn't understand what it is.
Sorry, which model?
Well, the big red.
Oh, the models that I'm highlighting in this slide. Yeah. So these models, essentially, they are describing a second component of this X-ray spectrum that can also be very prominent. That is not.
Núria, I think he's referring to the model where you're showing delta theta, delta t, right?
Oh, sorry. This one.
Yeah, credit J.
Okay. Yes. So essentially, what we're trying to set up is just a 3D cloud distribution that is going to be able to tell us simply the column density in our line of sight for a given angle, right? And then at a different, well, based on the mass of the supermassive black hole and a given time scale, you expect a certain rotation of these clouds based on the distance. So essentially, we're gonna be taking a bunch of observations, fake observations through these clouds at the same time scales that we actually have in the data. And we will see if we recover the same patterns that we're observing in the real data. Does that answer the question?
Well, so that picture is a picture of clouds that are surrounding an AGN, and the AGN is in the middle, is that right?
Yes, correct. That's what it would be, exactly. It's representing that. The AGN would be here. In this case, we would be seeing it from the top, right? And we would rotate in the direction of this arrow. So now we're looking through here, and in 10 days, it's a little extreme to rotate this much, but in 20 years, we would be observing from a different angle and see a different bunch of clouds, right? And depending on the sizes of your clouds and the distance to the supermassive black hole, 20 years is going to be enough or not enough to have exited one cloud, essentially.
Any final question? Okay, so with that, let's thank Núria again and Kenny as well. Thank you, and apologies for the technical issues, and just a reminder, we won't have a seminar